everybody. How are we all doing today? Hope everybody is doing well. Today our lecture is going to be on permutations. Now we're starting a new section here. This is all about what we call counting technique. And when I say counting, I don't mean like 1, 2, 3, 4, 5. This is a little bit more advanced than that. So this is a branch of mathematics called combinatorics. And combinatorics is just a fancy way to say counting. And the idea here is instead of 1, 2, 3, 4, 5, what we're looking at is counting how many ways certain things can happen. So remember going all the way back to the very first day, remember Pascal's triangle and the walking to work problem, and if you can go how many blocks over and how many blocks down, and we figured out how many different ways we could get there. And then we have the kid problem with the boys and the girls, how many different arrangements of boys and girls. Okay, that's what we're talking about here. How many different ways can we see something happen? And the first one that we look at is called permutations. Permutations. Let me see if I can find another pen there. Okay, so we're not going to do a definition right off the bat. What we're going to do is kind of start with an example and talk through it a little bit. So let's suppose that there was a club with 5 people in it. So a club with 5 members need to elect a president and secretary. Okay, hold on, this pen is, I am sorry, done. Poor pen. That guy away. Okay, so back to this. All right, so a club with 5 members needs to elect a president and a secretary. Now, I'm actually going to name the 5 members just so that we can see this the first time, but we probably won't ever name them again, okay? So let's say that we have Al, Bob, Carrie, Diane, and Ed. 1, 2, 3, 4, 5, there we go. Okay, so we've got five members of this club. Now, they need to elect a president and a secretary. Now, the first thing that we want to make sure is that we understand that everybody is going for it, okay? It's not like where someone's like, oh, I don't want to do it. They all want to be president. They all want to be secretary, okay? So the question is, how many different ways can this be done? And we're going to make a list here. So I'm going to put pres secretary like that. So one arrangement could be that Al is the president and Bob is the secretary, right? So it could be Al and Bob. But another arrangement could be that it's Al and Carrie as secretary, or Al could be the president and Diane could be the secretary, or Al could be the president and Ed could be the secretary. Okay, so there are 4 different options with Al as the president. Now, let's look at this again. Maybe Bob gets to be the president. So Bob could be the president and Al the secretary. Now, one thing to notice, are these 2 things different from each other? They are, because a president's job is different than a secretary's. So the order there does matter. Okay, now it could be Bob and Carrie. It could be Bob and Diane. Or it could be Bob and Ed. So there's 4 different options when Bob is the president. Okay, so can you see where we're going with this? So the next example could be that Carrie is the president with Al, Carrie with Bob, Carrie with Diane, or Carrie with Ed. So the hope is, like we've seen in the past, is we're looking kind of at a pattern here. So when we look at this again, couldn't there be the arrangements where Diane is the president, and then again over here where Ed is the president? And wouldn't they all have 4 arrangements underneath them? Everybody agree? So in total, okay, 4, 4, 4, 4, and 4 means that there are 20 different ways that this could happen. 20 different ways to pick a president and a secretary from this club with 5 members. But here's the dealio. I can make this way more difficult by doing one of 2 things. First off, what if the club had way more members? What if it wasn't 5 members, but 15 members? Can you imagine what a pain in the butt that would be? Okay, so one thing is that we started with a small club, so this wasn't too hard to write out. Also, what if I wanted to elect more people? What if we needed a president, a vice president, and a secretary? All of a sudden, this problem becomes more tedious. So as there are more things, either more members in the club or more people that we're picking, life gets trickier. So what we're going to do instead is we're going to use what we call a pigeonhole method. So pigeonholing and I don't really know where they came up with this, but the idea behind pigeonholing is that supposedly when you keep pigeons, they have their little holes in their nests, and they're all flying for the holes. And the idea is one pigeon gets into the first hole, and then all the pigeons then fight for the next one, and then fight for the next one. So what we're essentially doing is we're making holes, okay, pigeon slots or pigeonholes, and we're going to label this. So this is the president, and this is the secretary. Okay. So what we want to do is we want to decide, not this whole big thing, we just want to decide how many people, when we go to elect a president, how many people are vying for that first hole. And remember, everybody's supposed to be going for it, right? So we're going to elect the president first, everybody's fighting for it. So there are 5 different options. Okay, so we'll put our options. Now, we elect a president. It's Bob. Okay. Then when we go to elect a secretary, now how many people are vying for that? So there would be 4, right? Because somebody's already president. Bob is already president. So there's only 4 people left vying for the next one. And what would you do with 5 and 4 in order to get 20? So if we multiply those, don't we get 20? Okay, so this is the idea of pigeonholing, is instead of making a list, we kind of think about the list. So how many options did we have for the president? We had 5 of them, right? And then how many options did we have for the secretary? We had 4 of them. Okay, so it's kind of, without drawing all the options, it kind of makes it easier there. Okay, so let's go ahead, like I said, well, let's change this up a little bit. Okay, and change that into 15. Okay, so 15 members in a club need to elect a president and a secretary. So how many ways can this happen? Okay. So definitely not making a list here, okay? We're not going A, B, C, D, all the way through what it would be O or whatever. Okay, we're definitely going to use this pigeonholing. So again, we're making 2 slots, and again, we have the president and we have the secretary. But now, new club, how many people are vying for that first slot as president? Remember, we're supposed to assume all 15 want. So there are 15 options here. Now that we've elected a president, how many are vying for that secretary role? And that would be 14. Everybody agree? And just like we did over there, we multiplied, we'll multiply here. 15 times 14 equals 210. So there are 210 ways to elect a president and a secretary if you have 15 members. So notice how fast that grows. I mean, there's no way I wanted to list those. That would have been a real big pain in the butt. Okay. All right. So let's do one more. We'll stick with our 15-member club. But this time, our 15-member club, we need a president, secretary, and a treasurer. Somebody has to deal with money. Okay, so again, how many ways? Okay. So this time though, when we go to make our little pigeonholes, how many little pigeonholes are we going to have? Right, this time we'll have 3, won't we? So there's the president, the secretary, and the treasurer. Now, again, we're going to start off just like we did in the last one with 15 vying for the president slot and then 14 vying for the secretary slot, but now we have to give away one more job. So now how many people are vying for the treasurer slot? There would be 13, right? So if we multiply all of that together, 1 times 13 equals, all of a sudden this number gets huge. There are 2,730 ways, okay, 2,730 ways to pick a president, secretary, and treasurer. Wow, right? Okay. So this method that we're using here that we call pigeonholing, it actually has a proper name to it. It's called the counting principle. And the counting principle says this: if task A can be completed in M ways, and task B can be completed in N ways, then task A and task B can be completed in M times N ways. Okay. So basically it says that if you have tasks that you need to complete one after the other, task A, task B, in this case we have a task C, okay, then we can figure out how many ways in total if we multiply the ways that each one can be done. So it's just basically saying what we've just taught ourselves to do here. That's the fundamental counting principle, okay? So let's say that you had, we'll wait, we got another definition. So with the counting principle, now we're ready to actually define what a permutation is, okay? So we're ready for the permutation. We'll get rid of this. So we say a permutation of R elements selected from N elements is an ordered arrangement of those R elements selected without repetition. Okay. So a permutation is an ordered arrangement, okay, an ordered arrangement. And that's what we've done in these past couple examples. We've ordered, because we've got president and secretary, and we said that those two jobs are different. So there's an ordered arrangement. And the other thing that's important here is that it's selected without repetition. And what that means, like in our example, is that like Bob couldn't be both the president and the secretary. Once the person had a job, they don't get to have another job. Okay, so that's what a permutation looks like. It's just an ordered arrangement. So a good example is 4 people line up at the ATM. How many permutations, using our proper word there, are there? Okay, so let's make sure that this follows the rules here. Okay, there are 4 people and they're all fighting to get to the ATM first, okay? So there's an ordered arrangement, and that means that if you're one of the 4 people, where you are in line makes a difference, right? If you're first in line, woohoo! If you're fourth in line, not so woohoo. So there's definitely an ordered arrangement because the people are different people. And then the other thing is that there is no repetition, because once a person is in line, can they also be, if they're the first person in line, can they also be the second person in line or the fourth person? It doesn't work that way. So once one person has filled a spot, they are in that spot and there's no repetition for them. Okay, so we can find how many permutations there are by doing the pigeonhole method or using the counting principle. We're going to make 4 slots. 4 slots. And here's the ATM up here. So as people are rushing towards that ATM, how many people are vying for that first slot at the ATM? There are 4 of them, aren't there? Okay. Then, once someone is standing there at the ATM, how many people are vying for the second one? 3. For the third slot? 2. And then this poor last guy just goes, well, I'm last, and just lines up last. Now, the counting principle says that we're going to multiply those guys together, which will give us 24. Okay, so hopefully what you're noticing is this pigeonholing method. It works nicely, but what you're noticing is you see how the numbers start to cycle their way down? Okay, cycle their way down. And that's what we saw in all of the examples we've done so far. And that leads us to a new function for our calculator, or for ourselves, but it leads us to something that you may not have seen before. And that is n factorial. So n factorial says for any counting number n factorial is n with an exclamation point, okay, so that's the factorial symbol, n factorial. And n factorial is found by taking n times n minus 1 times n minus 2, and you keep going down until you eventually get to 2 times 1. So n factorial means to start with that number and multiply it by all the numbers less than it. So in this case, we started with 4, we multiplied by 3, we multiplied by 2, we multiplied by 1. So this is 4 factorial, okay, 4 factorial. Now, if I asked you to find 5 factorial, 5 factorial would be 5 times 4 times 3 times 2 times 1. So the idea behind the factorial is that we don't have to write that out, right? Which is kind of nice because it starts to get tedious, doesn't it? Now, if we did multiply this out, we would find that we got 120. But here's the dealio. If we already had 4 factorial, don't we already know that part there? So isn't 5 factorial just 5 times 4 factorial. Okay, do you see what I'm saying there? So this guy we can replace with the 4 factorial, or we could replace it by saying 5 times 24, and that gives us 120. Okay. So the idea here is to be able to kind of simplify your notation so that we don't have to write 5 times 4 times 3 times 2 times 1. So think about that, and let's look at something like 10 factorial. Now, do you understand what 10 factorial means? 10 times 9 times 8, blah, 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 down to 1. I'm not writing that out. Why would I write that out? And I don't even want to calculate it by hand. I don't want to go 10 times 9 times 8 in my calculator. But guess what I can do? I can use the calculator because guess what? It has factorial. So let's look at this. Okay, here is my calculator. So the first thing to do is to plug in the number 10. And then if we want the factorial key, you're going to go to the math key. See the math key here? Math. Then we're going to slide over to the one that says PRB. And do you notice how the fourth guy down is factorial? Oop. Hit enter, and there we get. So remember, it's math, and then over to PRB, and down to factorial, okay? All right, so when I put this in my calculator, I got 3628800. So 10 factorial is kind of a large number, isn't it? All right, well, let's even think about that a little bit more. What if we did 20 factorial? So go ahead and try 20 factorial in your calculator. And hopefully you noticed that right off the bat here, we went to scientific notation, didn't we? So I got 2.43 times 10 to the 18th power, right? So that means this 2, and then after this decimal place, there are 18 more, or so the 4, 3, and then 16 more zeros. So these numbers are huge, these factorial numbers. So anything we can do with them to simplify them will make life easier. Okay, so now finding how many permutations. So let's say that the numbers that we were dealing with were quite large, and we're still talking about permutations, but it's not something that we can do using our little pigeonhole method or something like that. We need a notation here. So finding how many permutations, the notation we use looks like this, NPR, okay, NPR. And if you're looking at the paper, the P is a capital P and the N and the R are subscripts, so they're below the line there. And to find NPR, okay, this is found by taking N factorial over, wait a minute, N minus R factorial, right? N minus R factorial. Make sure I write down the right thing. N minus R factorial. So we need an example of how this is going to work. So let's go back to our club again at the beginning. So let's say that there's the 5 club members, 5 members, and they need to pick 2 positions, president and a secretary, right? So we would write that as 5 permute 2, 5p2, 5 permute 2. And we know what the answer is supposed to be because we've already done this problem. So what we want to do is do it, though, using this formula. So the formula says to take the first number and put it up top, 5 factorial. Okay. And then on the bottom, we're supposed to go n minus r. So 5 minus 2 would be 3 factorial. Okay. Now, these numbers are not too huge that you couldn't figure this out just by doing the factorials themselves, but here's a common way to simplify. If we go 5 times 4 times 3 factorial, okay, do you see what I'm getting at there? 3 factorial, doesn't that just mean 3 times 2 times 1? So is this a way to simplify? I guess it's not simpler. but divide it by 3 factorial, and then look what happens. Boop, boop. And we have 5 times 4 left, which is 20. Look good to everybody? Okay, so let's say that we had a room has 24 chairs. How many ways can 36 people, wait a minute, that's too big, hold on. I won't make it too big. Let's go with 30 people sit in the room. Okay, so this one I asked a little bit different. So I gave you the room has 24 chairs, but I'm actually telling you how many people we have second. There are 30 people that need to sit in 24 chairs. Now, obviously, not everybody is going to get a chair. That's not our problem, okay? But we need to know how many different ways or how many permutations could we sit down these people. So we start with 30 people, permute 24 of them. So we're going to do an ordered arrangement of 24 of them. Now again, using the formula, okay, we can go 30 factorial over, and then we can go 30 minus 24 factorial. So this would be 30 factorial over 6 factorial. Okay. Everybody agree? Now, in this case, this is a little bit uglier than I had anticipated here. But the 30 factorial we're going to put on our calculator. But what I want you to remember is that in your calculator, this is going to be a huge number. So you kind of want to do this all at one time. So I would first find what the denominator is equal. And 6 factorial is equal to 720. Okay, 720. So now what I would do in my calculator is I would do 30 factorial, 30, and then go to the factorial. Don't hit enter, just immediately hit divided by 720. And I got 3.68 times 10 to the 29. So if we want to arrange 30 people into 24 chairs, okay, so some people are going to be standing at the back, but there are 3.68 times 10 to the 29 different ways we could do that. So we could have different arrangements for every day of the year for thousands and thousands of years. So that's an incredibly huge number that we've got going on there, okay? Right, so the thing to notice is that as the group size and the number of elements you're arranging, as they increase, life becomes very, 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 very large. Okay, so let's look at one more example though that we can do. Actually, let's look at a couple more examples that we can do without the use of our calculator. Okay. So without a word problem on this one, what if I just wanted you to find 10 permute 2. Okay, so we don't need a word problem or anything. So we got 10 elements and we're going to permute 2 of them, which means that, I know I erased the formula, but you should have it. So 10 factorial, and then on the bottom we do a subtraction. So 10 minus 2 is 8 factorial. Now again, without the use of our calculator, we're going to take this and go 10 times 9 times 8 factorial all over 8 factorial. And we stopped at 8 factorial because can these guys boop, boop. And then do we end up with 90? All right, how about this one? How about 8 permute 0? Okay, so let's say that there are 8 people in our club and we don't want to choose anybody. We have no positions to fill. How many ways can we do that? Now, this is a tricky one because the first you just go, oh, 0. Let's think about this a minute. Okay, let's write it out with the formula. That would be 8 factorial up top, and then we would subtract 8 minus 0 is still 8 factorial on the bottom. So what this equals is just 1, doesn't it? So if there's a 0, no matter what this number is here, 8 permute 0. If you want to permute 0 or choose nobody, okay, there's one way to do that. You just stand here and you don't pick anybody. Okay, we didn't pick anybody. So there's one way to do that. So if I had like 111 permute 0, does it matter that it's 111? Nope, you just stand here and say, I'm not doing anything. There's one way to do that. Okay, now, what if we had 8 permute 8? I don't know why I started with such a huge number, but that's okay. So 8 permute 8. Now I want to do this in 2 different ways. I want to go back to our pigeonhole method. 1, 2, 3, 4, 5, 6, 7, 8. So if we use the pigeonhole method, we have 8 people in the club, and we're basically giving everybody a job. So doesn't that mean that there's going to be 8 options for the first choice, 7, 6, 5, 4, 3, 2, 1. Everybody agree? So it cycles all the way down. So wouldn't that just be another way of saying 8 factorial? And I can't remember what 8 factorial is, and that's why I have my calculator. Math. Oops, I hit the wrong button. Which is 40,320. Okay, so we know that if you're going to take 8 people and you're going to permute them all, that's basically the same thing as saying 8 factorial. But what we need to do is also look at it in the formula form. So let's look at it again this way. That would mean to take 8 factorial over 8 minus 8 factorial, which is 0 factorial. Okay, got it? But here becomes an issue because we don't know what 0 factorial means. So what we know is that the answer should be 8 factorial. So doesn't that imply that 0 factorial equals 1? Okay, so by kind of showing the way that this should work, we can tell that if we use the formula, whenever a 0 factorial pops up, 0 factorial equals 1. We can make a little note there, 0 factorial equals 1. All right, so one more example here, and then we've got one last thing to do, and then we'll be done. Okay, so let's say that we have how many permutations are there of the letters in the word math. Okay, so this time what I want you to do is I just want us to rearrange the letters in the word math. Okay, it doesn't need to make another word, but like an example might be T-A-M-H. Okay, another one might be H-A-T-M. Okay, there's a lot of different arrangements. Some of them will make words, some of them won't, okay? So we want to make an ordered arrangement of those 4 letters. So essentially, wouldn't that be saying take the 4 letters in the word math and permute all 4 of them? Okay, 4 permute 4, which will be 4 factorial over 0 factorial. Okay, and remember 4 factorial is just 24. Okay, so that is a permutation. Now I'm going to ask this question, I'm going to ask the same question, but I'm going to change this up to make it a little bit harder. How many distinct permutations are there of the letters in the word mom. Okay. So this time I've got 3 letters and we're going to rearrange them. But the problem here is that this asks us for distinct, and that means that we're going to have a little bit of an issue. So using my different color pen, we could say like this could be M-O-M, like that. Now, color-wise, would that be different than this? Okay. Would we agree? Color-wise, the 2 M's have switched place. But if we're not using different colors and we're using the same color, how can you tell that those 2 have switched the M's? They are not distinct. So because there is a repeat, okay, a repeat, life becomes a little bit more awkward here. So we can do this. We could say that one arrangement would be M-O-M, mom. Another one would be O-M-M. Another one would be M-M-O. But there are no other arrangements, are there? Because the M's, like we could flip-flop these 2 M's, but they still look the exact same way. So when we go to do this, this one is not exactly a permutation, okay, because there is a little bit of a repeat. So a permutation means no repeat at all. So I can't use our P notation. So what we're going to do is we're going to kind of create a formula here for us. So we're going to go 3 factorial, and then what we're going to do is we're going to find the letters that repeat. So the M repeats. Now, how many M's are there? There are 2. So we're going to put 2. So this is how many M's? Okay. And slap a factorial on it. So what that means is that we're going to have 6, 3 factorial over 2 factorial, which is just 2, which means that there are 3 different or distinct permutations. And there we already wrote the 3 different ones. Okay. So when there is a repeat, life changes a little bit. So what if this had just been the word half? Okay. Now, do we have a repeat again? We do. So this one, we're going to start with all 4 letters, the 4 different slots, but we have a repeat of an H that shows up twice, so that'll be 2 factorial. And 4 factorial is 24, divided by 2 gives us 12. Right, so we can do this with small words that have repeats, but shall we go for a big one? Do you want to go right to the big one? Right to the big one would be M-I-S-S-I-S-S-I-P-P-I. Okay, so we want distinct permutations of the letters in the word Mississippi. So remember, that means flip-flopping these isn't distinct, so it means completely, so the word never looks the same, and it won't be a word anymore. So the first thing to do is to figure out how many letters there are in total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we start with the 11 factorial on the top. Okay. Then what we're going to do is we're going to go through and look for the repeats. Now, does the M repeat? It doesn't, so we don't worry about it. How many I's do we have? So we have 4, and we'll hit a factorial, and these are for the I's. But we don't stop there because we've got other repeats as well, don't we? So we're going to do some more repeats. There are also 4 S's, so we're going to hit this with another 4 factorial, and those represent the S's. Now, are we going to need one more factorial? We are, aren't we? The P's There are 2 of them, so we'll slap a 2 factorial on the end. So any repeat has its factorial, how many times it shows up on the bottom. Now, order of operations and using the factorial key means that doing this in your calculator straight in is very easy to make mistakes. So what we want to do is simplify the bottom first and then do the problem. So each one of these 4 factorials is 24, isn't it? 24 times 24, and then 2 factorial is just 2. So we're going to do that first. 24 times 24 times 2. So I've got 1152. Okay, so we're going to simplify the bottom of the fraction with these factorials, these little factorials first. Then, now that we have a single number on the bottom, now go to your calculator, find 11, up to math, over to PRB, factorial, and then immediately divide it by 1152. And I got 34,650. So if we wanted to reorder the letters in the word Mississippi and make distinct orders, there are still 34,650 different ways we can do that. Okay. Okie dokie. So let me make sure we went through everything. So if we want, this has kind of a formula, so we'll say distinct arrangements. Where we're going to take n factorial and we're going to divide by r sub 1 factorial, r sub 2 factorial, ... and these are for all of the repeats. Okay, so it's kind of a made-up formula, but that's what we basically did here. We start with the full number of letters, 11 factorial, and then we put the repeats, their factorials on the bottom. Okay, so that is the formula there. All right, what do you think? Okay, so when you go to do this, I want you to use your calculator, but I also want you to write out these fractions and stuff, okay? So I don't want you to get caught up on just using your calculator, because what if I ask you to do it in fraction form and I ask you to show your work? I need to be able to see that you know how to do that, okay? So practice doing them by hand, meaning making the little fraction, doing the little division. Try doing that as well as using your calculator. All right, you guys, so that is permutations. Sound good? Okie dokie. Have a great day.